Okay, so last time we introduced some concepts based on classification of matter and got a little bit into chemical and physical changes. We spent more time talking about chemical changes, so we're going to talk about physical changes in a little bit more detail this time. A couple things for review. Remember that physical changes involve no rearrangement of atoms. So the substances that you have before are the substances that you have after. There are no bonds breaking, no bonds forming. Okay? Excuse me, no rearrangement of atoms. And the way that we kind of view this from like our own observational perspective from like a large scale, because we can't often see what the atoms are doing, is we don't see drastic changes in physical properties. Now there could be changes in physical properties, but they're not dramatic. Okay, so an example of a physical change is a change in state or a change in phase. Okay, and we're going to look at information that really is on slide 6 of PowerPoint number 1. So if you want to, after this video, go and review that slide and be able to make the arguments that I make here yourself, then you know you've kind of got this concept down. So what I'm showing you here are 3 different states for a substance, and we're going to talk about the physical change associated with changing from one state to the next. So here we're going to have a solid, all right, and what we do to sort of signify that we have a solid is we use a parentheses and a small s. Here we're going to have a liquid, and we're going to use parentheses and a cursive L, and then here we have a gas. Okay, so this is a solid, liquid, and gas, and this is the scale that we would see. Like, this is the experimental scale. This is what we would see in the laboratory. Solids are generally these big chunks of things. Okay, liquids we have to contain, all right, and gases we have to not only just kind of contain with 3 walls, but we actually have to encapsulate them because they fly everywhere. Sometimes we see gases, sometimes we don't. It depends if they're colored or not. Okay, but we kind of have an intrinsic understanding because we exist in this world of what a solid, a liquid, and gas looks like. Okay, so we know that we can change from a solid to a liquid to a gas. And what do you do to make that change? Okay, you apply energy to the system. Okay, so to go from a solid to a liquid, everybody in here knows you would heat it. You want to try to get it to melt, right? That heating is actually adding kinetic energy, right? It's adding KE, all right? So when you see KE, that's kinetic energy. We know from other science classes that kinetic energy is the energy of motion, right? The energy associated with motion. So to go from a solid to a liquid, I have to make things move more, right? And the same thing happens from a liquid to a gas, okay? We're not rearranging atoms, right? But we are changing what the particles are doing in terms of their motion, right? So to go from a liquid to a gas, we're also adding kinetic energy, okay? We're making it move more, okay? Solids, right, then mustn't have, if you kind of look at what's happening here, solids are in the end where you don't have a ton of motion, right? Not a lot of motion. Liquids have kind of intermittent motion in terms of what's going on, and gases have a lot of motion, okay? So now let's try to explain this based on what happens on the atomic scale, right? The way that we view solids, right, and all I've done here is I've redrawn the different states, but now looking at the atoms and looking at what the molecules or substances might be doing, right? So here's a solid. And what we see with the solid and what the atoms are doing is that they're very organized. They're very close to each other, right? And it turns out that there are strong holds here. Now they're not necessarily bonds, okay? Each one of these guys is going to represent like a different particle, okay? But these guys are feeling each other. They're close packed, they're really organized, all right? And they're all tightly held. And because they're all tightly held, okay, there's not a lot of motion. There's not a lot of room to wiggle in there, all right? And so you get the properties of the solid by understanding what's happening with an atom. Solids, they have a definite volume. Well, that's because everything's really holding each other. It's not like it's just flying everywhere, okay? There's a definite volume associated with these guys feeling each other and keeping everybody kind of locked in place for the most part, okay? Solids resist change in shape, so a solid like a marker even, okay? If I just press down on it, it kind of maintains its shape. Well, that makes sense too if there's a bunch of well-organized atoms, all right, that are keeping its shape, maintaining really strong interactions, close, packed, organized structure. It's all about solids, all right? And that's how solids behave, okay? So let's add kinetic energy. So how do we go from a solid to a liquid? We make these guys move. And so if you have two solid particles and they're really interacting with each other, you start to make them move now, and they can move further away from each other. So hopefully you kind of see with this picture that it's not a close pack organized structure. This picture shows that, okay, we do have a liquid, we have something in a container, but the atoms now, they don't have a pattern, okay? They're further away from each other too. So that means they're feeling each other, but they're not feeling each other as much, all right? And then that leads to properties of liquids that we're familiar with, okay? We do need to put them in a container. They have a set volume. They do feel each other, okay? But notice they feel each other in a way that's not organized, not structured. You can see the definite difference between a solid and a liquid, right? So then what about going to a gas? Gases we need to contain, right? We assume that gases kind of occupy all the space associated with whatever container they're inside. They fill it up completely, right? We see from an atomic scale here that, okay, it looks like there's big distances between all the different particles involved. It looks like, to justify how this might happen, it looks like the particles might not be feeling each other much at all. So essentially what we've done is we've made the particles move so much that they're flying away from each other completely, okay? Now, all of this is a physical change. All of these instances of sort of going from a solid to a liquid to a gas, we're not breaking bonds, right? We're not rearranging atoms. We are changing how they feel each other, but again, it's not a chemical bond here. We're seeing what happens as these molecules either feel each other strongly, particles, right? These particles feel each other strongly or feel each other not at all. And then we have this intermediary with the liquid state, right? So it's all about motion, and the way that we control motion is by adding kinetic energy. Now, I mentioned it at the beginning when we were talking about this. We control kinetic energy through temperature. Right. And so an important definition is our definition of temperature. And temperature is a measure of average kinetic energy, right? So the way that we control how something moves, right, is by raising or lowering its temperature, right? So it's all about kinetic energy when it comes to temperature. And so you have to be able to talk about a solid, liquid, and gas from two perspectives, from what we see and from what the atoms are doing, right? And again, once you start to make arguments based off of what the atoms are doing, it's all about temperature as being the experimental control for kinetic energy. Right? So I just want to talk about one other physical change here with this video. And it's something that we mentioned last time, so it's another example of physical change. So now we're not talking about a solid, liquid, and gas state, but I do want to talk about a dissolution. Remember we talked about the physical change of putting salt in water, okay? So if I have salt in water, right, and this chemical formula for water is H2O. If I put salt in H2O liquid, right, what I get out at the end, right, it produces salty water. Remember we made these arguments before, okay, well, water is a clear colorless liquid, salt tastes like salt, I put them together, the properties are maintained, I get salty water, right? This means that this process is a physical process. We've made a mixture. Even though we're bringing two things together, we're not bringing them together in a way that's changing their chemical composition, right? So I just wanted to talk about this in a little bit more detail and think again about what happens on the big scale versus the small scale, right? So here is a container that has water in it. And let's take a chunk of just table salt. And table salt is sodium chloride. It's NaCl, okay, NaCl. And so what we do is we're going to throw this in there. And we know what happens. We made the point last time. What happens is it looks like the salt disappears. So if there's not a lot of salt, right, what we essentially get is something that looks like water, but now it tastes a little bit differently, right? This is actually changing the state of NaCl, okay? Because we know for sure this is a physical process, all right? Something is happening to the NaCl solid. Something is happening to that closed packed situation, right? Remember how we can view this solid here? This NaCl solid, and just use black. It's a bunch of NAs and Cls that are really close to each other, all organized, all right? That structure is actually breaking down, but again, we know that this happens in a physical way, okay? So we go over this in more detail later on in the semester, okay? Let's change this up just one little bit. Let's use blacks for NAs and let's use CLs as green. And here's NaCl, and we got a bunch of NaCl molecules in there, and they really are feeling each other strongly. They're solid. We dump them in there. A physical process occurs, but that physical process results in NAs and CLs floating away from each other because water has gotten in there and disrupted this framework, right? It's disrupted this strong organized structure, right? This physical process we call dissolution, and we actually invent a new state, okay? What we would say about NaCl is, yeah, it's still sort of NaCl. It's associated with water. It's acquired what's known as an aqueous state. So this is something that's a little bit confusing, but it's why I wanted to go over it. Even though the dissolution process looks like you're making changes to the structure here, all right, they are physical changes because essentially water is changing the state to what we can say is an aqueous form. So like I said before, we kind of get in more details this semester, more details next semester about how this occurs. But for you, like the take-home idea here is that you just need to make sure that you understand that whenever we talk about dissolution at the beginning part of this course or later on in this course, it's a physical process, right? One way that we know it's a physical process is we know how to actually reverse the process using just kind of temperature changes, right? If I have salt water and I asked you how we would go ahead and sort of separate it back into NaCl separated from water, you know that you could take this and you could take advantage of physical properties. If I wanted to separate this mixture, you would try to boil the water. Now, what would boiling the water do? Boiling the water would cause the water molecules to go away and you'd be left again with your salt particles, okay? So we can use temperature in that way to make the change, all right, back to the components, all right? And again, that's an indication where if we can use physical properties to get back to where we started, just physical properties, then what we're left with is a situation where we definitely had a physical change, okay? So this is actually reversible by taking advantage of the physical property of boiling point, all right? Now to drive that last point home, where we can take advantage of physical properties to separate things that are just physically intermingled, we could go back to sort of our simple example of a pizza. All right, and so if you have a pizza and you have some pepperoni on it, all right, we know that this is a heterogeneous mixture. We know that there's no bonds between, all right, the cheese, and I'm just going to color a little bit of it orange. There's not a sort of chemical bond between the cheese and the pepperoni, but these guys are physically intermingled. Well, just like salt and water, can we take advantage of a physical property of the pepperoni to go ahead and separate it out from the other component of this mixture, the cheese? Well, yeah, like pepperoni is kind of a solid. The cheese is in this like semi-solid liquid state, and you know, we're just dealing with solids, liquids, and gases this semester in aqueous states. There are more details associated with that, but that's all we have to know for this introductory chemistry course. But the cheese is kind of in this weird state where it's hard to pick up, but we could take advantage of the difference in physical property where that's pepperoni is definitely a solid. And all we have to do is, because it has different physical properties, because it's easy to pick up, that physical property allows us to kind of take it and just pull it away. This is the same idea of actually kind of boiling salt water to get salt in water. It's the same general process. You look for differences in physical properties, you take advantage of them, and you can bring the components back. So I just wanted to take some time, do a quick little video where we talk about physical changes as well. It's going to be important throughout the semester to determine whether a physical change has occurred or a chemical change. The changes in state that we talked about today are something we'll see again and again and again. And as always, just try to digest the material. Look at that slide 6. Make sure you can reproduce the arguments from today, and then you'll know that you're kind of set with understanding physical versus chemical changes.